Hi folks, welcome to part 2 of the February 12th virtual lesson. So now what we're going to do is we're going to try to determine the derivatives of the other basic trigonometric functions. All right, so I'm going to ask you to try these on your own first, and I'll give you a couple of tips here. Let's start with cos x. The idea is to try to avoid going back and using the limit definition. Okay, so the question is can I relate cos x to sine x? And this is where you might want to take a look at your identity sheet and see if you can find something that relates cos x to something involving sine. All right. Once you know cos x, well, then you can just use the quotient rule to find tan. And for cosecant, secant, and cotangent, well, hopefully you'll just use your derivative properties to help you determine those derivatives there. All right, so take some time to try to do as many of these as you can, and then turn the video back on. Okay, so we're back, and let's see what we can do here. So if you checked your identity sheet, you would have found ways to connect sine and cosine, in particular, those correlated angle identities. All right, so we can rewrite, and I'll use, I could use any one of them, but I'll use this one here. What I would say is the easiest one is you can rewrite cos x as sine of pi over 2 minus x. Okay, this expression here and that expression there are equivalent to each other. But that's useful because now I can actually take this derivative. Now I need to use more than just the derivative of sine, because this is not sine x, it's sine of a more complex input. In other words, I'm going to have to use a chain rule here. So if we let this represent our u, so first let's take the derivative of sine u with respect to u, and we already found out that's going to be cos u. So cos of, and u is pi over 2 minus x. Okay, and now we have to take the derivative of u with respect to x. Well, pi over 2 is just a constant, and what's the derivative of negative x? Well, just negative 1. All right, so we have a negative in front here, and now go back to those identities, and what is cos of pi over 2 minus x equal to? Well, it's just equal to sine x. Okay, and so what we have is another very nice result, that the derivative of cos x, which we would expect to be periodic, is just equal to, well, not sine x, but negative sine x. And in fact, if we take a look at the graph here, take a quick look. So here we have cosine of x. I have my slope of the tangent, and let's animate this point here, which is going to give us the derivative function, or we'll trace it. All right, so let's get these two together, and we see that as we move it, lo and behold, what do we get? Something that looks, well, not like sine, but like negative sine of x. All right. So not too surprising here based on what we're seeing geometrically, that the derivative of cosine is negative sine. All right. So let's now go on to the other ones. So once you have the derivative of cos x, you can now find the derivative of tan x by writing tan as a quotient. So sine x over cos x. All right, so let's apply the quotient rule here. So the derivative of the numerator is cos x, okay, times the denominator function, which is again just cos x, minus the numerator function times the derivative of the denominator function. We just found that the derivative of cos x is negative sine x, okay, all over the square of the denominator. All right, but I think you see where this is going, because when I simplify the top, I have cos squared x plus sine squared x all over cos squared x, and of course cos squared plus sine squared is just equal to 1. So we have 1 over cos squared x. But we can go even a little further, because 1 over cos x is the same as secant. So this is just secant squared x. All right. So perhaps not quite as nice as sine and cosine, but again, it's related to another of our trig functions. All right, let's keep going. Let's now find these derivatives of cosecant and secant. Again, we're not going to go back to the limit definition. We're just going to use our identities, because I can write cosecant as 1 over sine. But even better than writing it as 1 over sine x, I'm going to write it as sine x to the negative 1. Now notice here how I put the negative 1 on the outside, because I don't want to confuse this for the inverse of sine. Okay, I want this to be the reciprocal of sine, so we have to be careful with our notation. The reason why I want to write it in this fashion is because now I can use the chain rule again. This is going to become our u. So what's the derivative of u to the negative 1? Well, it's negative u to the negative 2 times the derivative of u, which is cos x. All right, so let's clean this up a little here. So we've got in the numerator negative cos x, and in the denominator sine squared x. So again, we see that this derivative is related to trigonometric functions. Now, this is normally not how we express the derivative of cosecant. We tend to rewrite it, and we split up the fraction in a clever way. Okay, so what we do is we're going to rewrite this as 1 over sine x, okay, times cos x over sine x. All right, and now let's see what this looks like. Well, hey, wait a minute. 1 over sine x is just cosecant. So isn't this nice? That same function reappears. And here, cos over sine is just equal to cotangent. All right, and this is how we normally express the derivative of cosecant x. Okay, cosecant x's derivative is equal to negative cosecant cotangent. All right, now I'd almost say you could have made a conjecture as to what the derivative of secant would be given this result. Well, let's see what happens. So again, I'm going to rewrite this not as 1 over cosine. I'm going to choose to write it as cosine of x to the negative 1. Oops, taking the derivative there. All right, and so again, I'm going to apply the chain rule. So this is going to be my u. So derivative of u to the negative 1 is negative 1 u, which is cos x, to the negative 2, times the derivative of cos x, which now we found was negative sine x. All right, and now the negatives cancel each other out. So what are we left with? We're left with sine x over cos squared x, and I'm going to do the same thing here. I'm going to split this up into 1 over cos x times sine x over cos x, and that's just equal to secant of x tangent of x. Okay, so we're seeing a bit of a pattern here. Okay, the function again repeats itself, except this time multiplies tan as opposed to cosecant, which repeats itself and multiplies cotangent. All right, and the last one here is going to be the derivative of cotangent of x, and not surprisingly, so I could write this as the derivative of 1 over tangent, but I think what I'm going to do is I'm just going to stick with cos x over sine x. All right. Oops, sorry, we're finding the derivative of that. Want to make sure our communication is good. So let's apply the quotient rule here. So derivative numerator, cosine is negative sine x times the denominator function, which is sine x, okay, minus the numerator function, cos x, times the derivative of the denominator function. Derivative of sine x is again cos x, and I think you're going to see some nice stuff is going to happen over the square of the derivative. Okay, here I'm going to factor out a negative 1 so that I'm left in the brackets with sine squared x plus cos squared x, which of course is equal to 1. Okay, so we're left with negative 1 over sine squared x, which can be written, and again, if you look at the derivative of tangent, I don't think this is going to be too surprising, equal to negative cosecant squared of x. Oops, cosecant squared of x. All right, and so here we have the derivatives of all 6 basic trigonometric functions. Okay, now I want you to look for some patterns here. notice tan and secant are related. The derivative of tan is secant squared. The derivative of secant has a tangent in it. Okay? And cosecant and cotangent are related. Okay? Derivative of cotangent is negative cosecant squared, and the derivative of cosecant contains a cotangent and also the negative. So these are ways to help you remember the patterns. All right? So the last thing we're going to do for this lesson is to try to apply these rules to finding derivatives. All right? So you should take some time, pause the video, and try to solve these derivatives. And of course, it doesn't just involve these trig function derivatives, but also using the chain rule and using the quotient rule, maybe using the chain rule more than once. All right, so pause and try these out, and we'll be back in a second to determine them. Okay, so we're back. Hopefully you gave these a try. So let's see what happens here. So if I want to find f prime at x, all right, here I see that I have a sign, but of a more complex input. So this is going to be my u. So first, the derivative of sine u is going to be cos u. So cos of x cubed minus 3x. And then we multiply that to the derivative of u with respect to x, which is 3x squared minus 3. Okay? Now, if you want to be certain that this expression is not inside the cosine, you might want to put square brackets around there. Okay, so this represents the derivative of sine u, the derivative of the outside function, and this represents the derivative of the inside function. All right, let's move on to b. Okay, clearly here we're going to have to use the quotient rule. Okay, but in using the quotient rule, when finding the derivatives of numerator and denominator, I'm going to have to use the chain rule. Okay, so let's start with the derivative of the numerator. So I'm going to think of this as u squared. Cos x is my u squared. So what's the derivative of u squared? 2u. So 2 cos x. Okay, and then times the derivative of u, which was cos x, is negative sine x. Okay, times the denominator. So we see this is getting pretty long. I'll probably be going straight right through. Okay, minus the numerator function, cos squared x, times the derivative of the denominator. Well, again, now I'll call this v. It's v to the 1/2. So what's my derivative look like? Well, 1/2 v, which is 3x to the negative 1/2. Okay, times the derivative of v. Don't forget that. Derivative of 3x is 3. Okay, and of course, I have to divide by the square of my denominator function. Okay, now obviously if I were simplifying, the square of the square root would just give me 3x, but unsimplified, we can just leave it like this. All right, and then lastly, part C. So let's find the derivative here, and I think I might rewrite this to make it look a little easier to work with. So instead of writing cube root, I'll write this as an exponent 1/3. So I have tan of 2x all to the 1/3. Okay, so again, we start with our most exterior function, which is x to the 1/3. So this whole thing here is going to be my u. What's the derivative of u to the 1/3? Well, it's 1/3 u to the negative 1/3 minus 1 is negative 2/3. Okay, times. Now we're going to find the derivative of this inside function. But again, we're going to have to use the chain rule again because I don't have tan x, I have tan of 2x. So that's going to be my v. So what's the derivative of tan v? Well, it's secant squared v. So times secant squared v, which is 2x. And then lastly, find the derivative of v with respect to x, and the derivative of 2x is just 2. All right, and so this is the derivative here. So just to recap, okay, you can find each of these other derivatives, okay, knowing the derivative of sine x, okay, without having to use the limit definition. So using these derivatives and of course our derivative properties. And here we see that we can apply our derivative properties, whether it's the quotient rule, whether it's the chain rule, whether it's a subtraction rule, just as we had with the previous functions that we worked with. Okay, so that's it for this lesson.